Good morning, SIGGRAPH. So I am Javier van der Palen. I direct research and development at Activision Central Studios in Santa Monica. We put together this course with Paul Debevic's group at the ICT with the purpose of showing you the projects that we did together last year on Digital IRA. The Digital IRA project was presented at various venues in pieces throughout last year. First, at GTC, NVIDIA, and the ICT demonstrated the power of their capture and the graphics of NVIDIA. Subsequently, Activision R&D demonstrated at GDC that we did not need beefy machines to do high-quality work with the great data that the team from ICT has provided us, and a little bit of clear thinking about how to art direct and code shaders. Then at SIGGRAPH last year, Graham 5 and the ICT presented their method of capture and tracking. As well, we presented at the Real-Time Live everything together. But this project has never been presented together, so this is the purpose of this group, is to take it from the very beginning to the very first capture to the rendering of the last pixel, and just show you how we did it, how this can be achieved. Now, we think that this is an accomplishment, what we had last year, but it was not developed in a vacuum. We drew on concepts developed on computer graphics, animation, and computer vision, animation, and graphics through the last 2 decades. So there's a lot to draw from that. But it is, in a small way, a culmination on a research on human animacy. Both computer vision and shading work have been done achieving this quality, as well as animation, achieving this quality or sometimes higher. But to my knowledge, this is the first time that we put together all these things in a runtime setting. So this is what we're going to talk about today. Lessons from this that I learned is that it's not sufficient to capture a human perfectly to the tenth of a millimeter, or to be able to track this human perfectly. It is not sufficient to render a character statically in beautiful light, or even understand how the pixels change with animation, but you have to put it all together, and you have a very good eye for art to understand when you're doing something wrong. So this is what we did last year. We think that we are approaching the uncanny valley. We really have not crossed it, but I think that the threshold is visible to all, and I think it will be crossed multiple times in the very short future. I am going to go through here. So this is Ira. He volunteered himself to become our digital character. And we are going to show you now a video that was cut last year by the ICT on this, on how this was put together. This little video is a quick prelude to what is going to be shown, and it will speak for itself. So the purpose of this project is not just to get the highest possible quality, but as well to compress it to the game and to the game, the world. Now, this is the work from NVIDIA. Just go much further. All right, so I will cut it here. So the Digital IRA course, I'm going to give you a brief overview and then hand over to Paul. The first half of the course deals with vertices, mostly with the capture and then the compression. So first, a speaker is going to be Paul de Bevec, and he's going to talk about his work on facial scanning and all the work that ICT has done to try to capture these characters perfectly. The second speaker is going to be Graham Fife, and he's going to talk about how we get this beautiful data animated, followed by Etienne Danvois. Now, Etienne is with Activision Research and Development, and he took this data and compressed it so that we can actually put it in our current generation, or actually last generation. Engine. After the break, we are going to follow up with the pixel animation pipeline. Etienne will continue with that talk, and then we're going to talk about the work. Jorge Jimenez is going to talk about the work on skin shading and eyes, followed by a live demo from myself. And then our last speaker will be Hao Li. We invited him because when we set this course up, I intended to have his runtime capture and our runtime render work together. But this actually hasn't happened yet. However, Hao has a lot of good insights about the future of where we're taking this. So we start with very high resolution, mostly intended for film. We take this data, we make sense of it in the realm of games, and Hao is going to try to bring us down to the realm of consumer level applications, which is the real future. So with this, I introduce Paul.
All right. Are we still microphoning here? Awesome. Very good. Hi there. So my name is Paul de Bevec, and I work at the USC Institute for Creative Technologies. And this was a very exciting thing to get to be part of the Digital IRA project. And we've been talking to Javier and his group for quite a while, probably over the course of a year or so before we even started this thing, saying we should try to do something. You know, we kind of know something about how to animate and render faces, and you guys know something about how to scan faces. Why don't we try to put this together? And the part of the course that I'm going to talk about is work that our lab has done in the areas of facial scanning, also microgeometry capture, and facial scan correspondence, which all ended up being relevant to what we did in the Digital IRA project. So, Digital IRA, as you've probably surmised, is based on real scans of a real person. The person who is scanned is Ari Shapiro. He's a graphics researcher at the USC Institute for Creative Technologies, and he will actually be presenting some of his group's work in real-time live on Tuesday late afternoon. Automatic, very rapid capture of avatars and automatically rigging them to go into game engines using a Kinect-based capture. So that should be a very nice demo. He graciously, or perhaps unwittingly, agreed to come into our Lightstage X system and get scanned to become the facial data for Digital IRA. Actually, it wasn't even, I don't think we even knew we were going to do Digital IRA at the time, and you can see we switched his name from Ari to Ira when he became digital. It's kind of like a data and lore thing, if anyone's seen Star Trek. The scans look something like this, and I'm going to tell you about how we got these scans. So we wanted to be able to produce data that could be rendered, well, by sufficiently powerful algorithms and thought and people in a game engine. And we wanted to capture, ideally everything that we need to do a pretty realistic version of Ari Shapiro in there. So our scanner now covers ear to ear, and it gets a high-resolution map of geometry. These start as up to 15 million polygon meshes, and then they can be reduced and turned into that plus a normal map or that plus a displacement map. And very importantly, they come with a texture map as well. In fact, they come with a diffuse texture map and they come with a specular map. And so you have a lot of the source data you need to put into your skin shader, the high-resolution geometry, the spatially varying surface texture, and the spatially varying specular reflectance. The key, though, is that we didn't just scan Ari in one expression. We scanned him in many expressions. And this is most of the data set that was scanned for the Digital Ira project. It's 30 expressions. Each one here is actually shown 3 times because we see it from the rendered from the front and then kind of from the 2 sides. That's how we normally output our previews of a scan, so we can check that it looks good ear to ear. And as you'll hear in further talks, we didn't use every one of these expressions in the real-time digital version. That would be a little bit too memory intensive, but we were intelligently selective as to which ones we used. And a couple of them here were just, you can see, designed to get teeth textures down in this area as well. But it's a bunch of facial expressions. They all come with their own texture maps as well. And the idea is to kind of elicit most of what the face can do. Oleg Alexander, who's part of our group, and he was part of ImageMetrix before, helped design the set of facial action coding system expressions that we would capture. And in fact, the previous time that we had done this kind of project was with the company called ImageMetrix that did facial animation. And back in 2008, at SIGGRAPH 2008, we showed a project that was called the Digital Emily Project. And that used a previous iteration of the light stage called Light Stage 5 and about 30 facial expressions of Emily to do a relatively realistic face replacement. And back in 2008, it was a bit of a stunt even to do this kind of work in an offline rendering situation. But Emily's face didn't go even quite ear to ear. It went kind of almost to the ears. It was a face replacement over regular video. And it didn't have the rest of the head. It also just didn't render in real time. We actually tried to do a real-time version of Emily from that data set back in that era, and it just didn't look very good because it didn't have the right skin shaders, in particular stuff going around the eyes and the mouth just didn't work. And that's one of the things that by working with Activision, you'll see some of their solutions that finally got this kind of thing to work pretty well in real time. So I thought I'd say a bit about how the facial scanning system works. It's based on what we can photograph in a light stage. The early versions of the light stage lit a face one light direction at a time and came up with a vast database of skin reflectance functions. And so you could actually computationally relight a face by adding together lots of images lit from different directions. Well, that was a pretty expensive capture because you'd be taking hundreds of images of the face in every expression to get all the different lighting directions. So nowadays, we illuminate based on the gradients of illumination. There are these, our favorite 4 lighting conditions. It's basically the first 4 spherical harmonics, and we can reproduce these using the intensity control in this sphere of lights that we have in the light stage. So over here in the upper right, you can see this is a face lit from full on, all light from every direction, very flat lighting. And then these 3 images here are gradients of light, where the lights in the light stage are, for example, here they're bright on the top, and then they get lower in intensity at the equator, they're half on, and then at the bottom they're all the way off. So it's a gradient of light top to bottom, gradient of light right to left to right. For a bit better signal to noise ratio, and actually in a way that it helps us line things up, we'll also shoot the reverse gradients these days. So not just right to left, but also left to right and bottom to top and back to front. So that's 7 lighting conditions. And the key observation that was done in our Ma et al. EGSR 2007 paper is that the ratio images here, if you take this image divided by this image here, the skin color is going to stay basically the same color from here to here. But the response to the directionality of the illumination is going to change because this is lit from the side, this is lit evenly from everywhere. So if you divide this image by this image, it divides out the skin color, and it leaves you basically with a map of how much the face responds to light coming from the right. And in fact, with some very simple math, this becomes the x component of the face's surface normal. Just like this image, which is the y gradient divided by the full-on, is the y component of the surface normal and the z component of the surface normal. And you can come up with this color-coded normal map where the red, green, blue value in the map indicates the XYZ unit vector that little pixel of skin is pointing. And this is where we're going to get the high-resolution detail. Now the problem is that faces scatter light, they're semi-translucent, so the light that hits the face tends to blur out by a millimeter or two before it diffuses back out of the skin. And so the amount of detail that you'll get with this technique is limited because it blurs out the illumination. And that's why we put polarizers on the light sources. And we showed even back in the Digital Emily days by putting static polarizers on all the lights and a polarizer that switches back and forth for the in front of the camera, the front camera, we can actually cancel all the specular reflections. Cross-polarized light will basically eliminate specular reflections because the shine of the skin will maintain polarization. If you put a cross-polarization condition on your camera, it will block the shine. The light that gets under the skin, which undergoes multiple scattering, will diffuse out unpolarized largely, and that'll still make it through either polarization direction. And so the result is that you can get one image where the specular shine is gone, another image where the specular shine is present, and you subtract the subsurface scattering off of the image that has subsurface scattering and specular, and you get images of just the specular reflection. And this is important because this light doesn't scatter within the skin. It's a first surface reflection, and it's going to be our best record of the detailed surface shape of all of the skin texture. So if we zoom in on these specular images here, this is, again, Emily's face. You can see that we have an enormous amount of detail that we can see in terms of skin pores and fine creases. And if we watch the different gradients of illumination, we can see that the way that the light plays off, I'll go back through these again, the way that the light plays off of the shine of the skin is going to give us a good map of the fine scale skin detail to skin pores and fine creases. And that gives us a high resolution surface normal map. So at a local level, this is going to be our cue as to the high resolution detailed shape of a face. The low resolution detail back in Digital Emily days came through structured light. We'd have a stereo pair of cameras at the front. We'd put on some stripe patterns so that we can easily correspond pixels from the left image to the right image. And then we can build up geometry that has the right basic shape from the structured light patterns. And then we emboss it with the detail that comes off of the surface normal recovery from the specular component, and it produces scans that are nice and high resolution like this. Now you'll notice though that these scans are missing the ears and they only go a little bit past the cheekbones, and that was one of the challenges we had to deal with Emily, that by the time we got to Ira we were able to fix that quite a bit. The problem with the earlier scanning technique, MA 2007, is that it really only worked for a camera that was right in the front. So this camera here had a glass polarizer that would flip along the 45-degree axis that would turn it essentially from a horizontal polarizer to a vertical polarizer back to a horizontal back to a vertical, which is actually a little slow to do that mechanical flipping. And the pattern of polarization directions to cancel out the specular, so here if this is a horizontal polarizer, we need to put mostly vertical polarizers on the stage, but due to the index of refraction of the skin, where the Brewster angle is, you actually end up with, if this is the front, a kind of funny swirly pattern that's not front to back symmetrical and certainly not radially symmetrical, not around the y-axis of polarization. And so you can cancel out the specular from the front but not from the sides. So if we needed to scan an entire face, we couldn't just put cameras off to the sides and still get our polarization tricks to work. So back in Digital Emily days, and also what we did for the work that we did on the first Avatar film, is we had to scan the actor 3 times from the front, and then we'd have to reposition them to the side and get a scan from the right and to the left. We did that for Emily's neutral expressions, and we were able to put this together. Still didn't quite get the ears, but again, Emily was just a face replacement, so her ears stayed from the original video. But we didn't do it for every single expression because that would have been a huge pain to turn her for all 30 expressions. And also, facial expressions are harder to make exactly the same way on several scans when you would turn people. So we had this issue that we had a lot of these nice facial expressions that really didn't get the rest of the cheeks. And a lot of the work the Imagemetrics had to do with our data is to correspond them to the full facial scan and add in the rest of the cheek detail to get all of those blend shapes. So fortunately, by the time we did Digital Ira, we had done a research paper, Abhijit Ghosh et al. At SIGGRAPH Asia 2011, where we figured out a different way to do the polarization to get multi-view capture to work and to reliably. Here we were just using 5 cameras, and by the time of Digital Ira we were using 6 to get this. And we figured out that if you change the polarization, instead of at the camera flipping a polarizer, to flipping the polarization on the stage, that you can actually get something that is symmetrical around the y-axis and will let you cancel out and bring back the specular reflection from the whole sphere at once for any camera that's basically somewhat near the equator. And the 2 polarization patterns are basically lines of latitude and lines of longitude on the stage. So one pattern has vertical polarization everywhere, the other one has horizontal polarization everywhere. And it's not 100% perfect cancellation, but it's about 98% perfect, and that's plenty good enough for what we're doing for analyzing skin reflectance. The challenge was, though, we had to somehow create a light stage where the lights could magically change polarization. And what Abhijit did for first is he took the lights of light stage 5 and he moved the polarizers on them so that every other light was polarized horizontally, vertically. And that meant it kind of decimated our lighting resolution a bit, but it was okay. So that's the horizontal pattern. Then we switched to the vertical pattern. And you can see the 2 faces there. This is cross-polarized. That's parallel polarized. It brings the specular in and out. So we could do that on light stage 5. Another thing that helped what we did there is we also addressed a problem that we had with Digital Emily, which is that specular reflections actually get brighter as you get to the grazing angles. And that's certainly just as true under polarized light, even more so. In the great words of Chris Nichols from Chaos Group, everything has Fresnel, and traces certainly do. And what we need to compensate for is the fact that we really want our maps not to get brighter around the edges. So in fact, you can actually, since we have a record of what the surface normal is from our gradient illumination everywhere, we can tabulate the brightness of the reflection versus the amount of the angle away from the camera that we're observing it, and then figure out for the face in a data-driven way how the brightness increases as you curl away from the viewpoint. And then you can essentially fit that function and invert it, and then it produces an image that takes out the effects of the Fresnel gain that you can see. So these are 2 images. One's been corrected for Fresnel gain and one hasn't. And that's an improvement we've made to our polarization process. And that's helpful because the stereo correspondence algorithm that Graham Fife wrote, and he's going to be up here to talk about facial animation techniques shortly, uses the diffuse color of the skin everywhere, which is very view independent under this multi-view process. It uses the specular intensity as well, which now that this is Fresnel compensated, it's much more photoconsistent from view to view, so you can do correspondence using that component. And then, of course, we also use the specular surface normals converted to world space to correspond all of this. So it's now a unified solve for photoconsistency between the different maps from the different views, and to have the local surface detail match the photometric information from the gradient illumination to get the high resolution surface. So it's a unified solve for the detail as well as the overall shape of the face. And this is done over a cylindrical space and gets our final result like this. Another thing that we've done since Digital Emily is that we had a Transactions on Graphics paper by Cyrus Wilson et al. That's called photometric alignment. And one of the things that you might have noticed in Emily's scan, that there were a bunch of dots on her face. We kind of put those on last minute just in case she moved during the scanning process, because it takes a couple of seconds to shoot the photographs that we need to capture an expression. And we realized that we could mark the points over the course of the expression capture and then stabilize the footage based on that. But we didn't really enjoy marking up actors' faces. it would have been much better to do this just using optical flow to figure out how the face moves from expression to expression. But unfortunately, the lighting is changing, so it's hard to do optical flow from these different image sets here. So what we realized is that if we put special lighting conditions into the sequence such that some lighting conditions add up to other lighting conditions, for example, the right gradient plus the left gradient equals the full-on condition, we have some constraints on optical flow so that this image flowed to that image plus that image flowed to this image should equal that image. And then we can have some photo constraints on that. So that's another reason why we shoot right to left as well as left to right gradients, not just signal to noise ratio of the surface normals, but also so that we can post-flow this. And this has even been extended to performance capture as well, where people can intentionally be moving during the gradient illumination sequence, and we can stabilize that and get all the maps that we want. So these were some maps from the SIGGRAPH Asia paper. Got some nice expressions there, good skin detail. And even better than that, by the time of Digital IRA, we had also built LightStage X, which is a somewhat larger version than LightStage 5. It had somewhat more lights for better specular reflection, and most importantly, thanks to some work by Xiuming Yu in our group who designs our electronics, it has these light sources that can change their polarization from horizontal to vertical within the same light. And basically the center of these lights have 12 bright white LEDs. The corners have color LEDs so we can literally light people with HDRI maps and play lighting back on them. But for facial scanning, what we do is we put interchangeable filters over here, and we're able to get different polarizations to happen. I'm kind of turning a polarizer in front of these things. All of our light sources have polarizers on them. Some of them are polarized vertically, some of them are polarized horizontally, and so we can switch the polarization at the light source very rapidly. No moving parts, no glass polarizers flipping in front of a camera and potentially flying across the room. Not that that ever happened. And so then we get these nice scans, fully ear-to-ear, of our actors. And in fact, if you want to see an example of LightStage X technology, there's a new LightStage in existence called the Portable LightStage, which is built by our technology licensee Otoy, and they are at the SIGGRAPH Expo in booth 1447. So just go in past registration, off to the right, you will see a nice light stage with these LightStage X light sources all lit up. So the second thing I wanted to talk about is some work that we did trying to look at even higher resolution detail of skin. And this was kind of speculative research at the time to just try to look much closer at skin and figure out, is there anything even beyond the level of resolution we're seeing with LightStage X that could be important in skin rendering. And this is stuff that was became a Eurographics 2013 paper by Paul Graham et al. And we were noticing that we do get a lot of facial detail in our scans, but compared to a real photo, and this is probably hard to see from the back of the room, I apologize, we will be zooming in on these in just a short order. Real photographs have a lot more kind of crunch and detail to them, like little micro glints are showing up in the face in terms of the specular reflections, and it really helps the skin seem a lot more alive and realistic. And you might not see that from far away, but when you get close in on a face, there's really a lot of very interesting stuff and no limit to the amount of detail that you can see as you look closer and closer in on skin. So we thought, wouldn't it be great if we could capture 10 times as much detail in a LightStage scan? Well, we're probably not going to be able to do that with the current cameras. We're not just going to be able to buy cameras that have 10 times as many pixels in both dimensions. But what we could do is we could move the camera much closer to the face and capture just a patch of skin at much higher resolution. So we did two versions of this, one where we built a miniature kind of half LightStage out of 12 extra lights that we had. And we put a macro lens on our camera so we can zoom in really close. And then we realized we can also just put the whole camera inside the LightStage, about 20 centimeters away, and then focus on the face. Now the problem is when you're so close, you really need to push your depth of field pretty far on this. So we have this little metal plate with an aperture cut out of it that you push part of your face up against, and it holds your face at the right distance to the camera so that we can then run our polarized gradient illumination conditions and do a high resolution capture. And of course, it's going to switch between the vertical and the horizontal polarization conditions. That's especially important at this scale because the subsurface scattering is quite large in distance compared to the detail that we're trying to capture. And we're really trying to capture hundredths of a millimeter. That's 10 microns, or 10 millionths of a meter. And it's possible to do that because the pixels on a digital SLR camera are just a few microns wide. If you put a macro lens on, like a 100 millimeter 1-to-1 macro, it means it's taking 1-to-1 size of thing that you're photographing onto size of the sensor. So if your pixels are 7 microns wide, which they are for our camera, then you're seeing 7 microns in each pixel when you're imaging the skin. So when we take those lighting conditions, it kind of looks like this in the aperture. This is showing on Paul Graham's face where these came from. And you can see the lights playing off of the skin. The specular component is accentuated. You see stuff that you didn't really want to see in your skin, and then go for facial treatments afterwards. But after a little processing, we get these skin patches at very high resolution. And we can visualize those in two ways, one of which is kind of a shaded map based on the surface normals, the other which is just as a displacement map where darker means pushed in like a skin pore and brighter is like a little bit of a bump. And this is, I think, Paul Graham's face, and we're looking at 5 different patches: the forehead, the temple, the cheek, the nose, and the chin. And something that we discovered is that all 5 of these different areas actually have quite different skin microgeometry. And different people, so this here is a female subject in the LED sphere, they have different sets of facial textures as well. But actually going from 2 very different subjects, subject A's forehead will look more like subject B's forehead than subject A's forehead will look like subject A's nose or subject A's chin. There's more variability around the face typically than there is between individuals. But it's nice to be able to get these things for the actor that you're actually scanning. Now the idea was then we would use texture synthesis to up-res a facial scan so that we would have all of this detail across our entire facial surface. And since we're getting 5 different surface areas, what we have to do is take our high-res displacement map, kind of cut it up into different areas, and each one of these areas is going to get synthesized up using a different key sample of skin to provide the examples of the detail that you want. So fortunately, there's been decades of great work at SIGGRAPH in the area of texture synthesis, including constrained texture synthesis, where you're basically, this here is a zoom in of one of our light stage scans, and we're trying to take the low resolution detail you see down here and turn it into high resolution detail that you see up here. It's kind of scanning across slowly. And it's doing that by, for every region here, using the image analogies framework by Hertzman et al., looking for an area in our high resolution sample that's basically the same for the low frequencies, and then borrowing the high frequencies from that skin sample to inject into the otherwise just kind of medium resolution scan. So we found by doing this, we can basically increase the resolution of our light stage scans by a factor of 10 or so, and go from 1/10 of a millimeter accuracy to about 100th of a millimeter accuracy. So that's scans before, this is scans now on the left to the right. And we just lost the video signal, which we were a little worried was going to happen. Oh, we're back, great. So we just zoomed in on Connie's face there. And there's Paul Graham. I think we're going to look at his forehead. So that's before. You zoom in, it kind of just gets boring and blurry. The microgeometry scan will get keep all the resolution. And of course, these are relightable, and you do get to see nice, satisfying glints happening there. And if you like microgeometry, there's going to be a talk that our graduate student Koki Nagano is going to give, and that is going to be on Wednesday in the morning in the Hair Today session. And this is about using this microgeometry capture process to capture dynamic microgeometry. So the skin looks interesting when you zoom in on it. It looks even more interesting when you zoom in and squish it around. And there's actually quite a lot of very interesting dynamic effects that happen. And we're able to capture this in real time. So the final thing that I wanted to mention today is a tool that really helped Digital Ira come to be called Vuvuzela. And this is a tool that will match the UV texture space from one facial scan to the next. And when we were naming it, we looked at all the words that have UV in it twice. And the one that wasn't a part of the anatomy we didn't want to keep saying was Vuvuzela. And the Vuvuzela tool basically works like this. You are going to feed into it 2 of your favorite facial scans. And one of them might be like a happy expression, the other one might be a neutral expression. And you could just try to do straight out optical flow between the 2 UV spaces. It doesn't always work, and in particular, when you start seeing surface detail show up, when people smile, they get wrinkles around their eyes, or there can be actually quite a lot of stretching around the mouth. These things, nothing that we wrote ever worked completely automatically, and that was kind of a bummer. So what we did is we built a semi-automatic artist-driven tool. We had a poster about it at last year's SIGGRAPH, so on our website there's actually something you can read about this thing. And what you do is you start by marking some points on one scan. You mark not exactly the same point on the other scan, but close enough. And that gives the optical flow an initial estimate. And then you get a final expression on the right that will show the map. And you can switch between the different, you can blend shape like you're seeing here, between the different expressions to make sure that you've got pixel level accuracy, that these scans will line up with each other. And if you didn't have that, then you wouldn't be able to build your blend shape facial model, which Digital Ira really leverages being able to do that. And the result is that you can actually look and watch the scan to see if just the geometry transitions correctly from one pose to the other. You can also see on a static face how the texture map will change from one pose to another. And it'll become very clear that the diffuse texture of the face will change a lot from one expression to the next, because blood is going to flow into certain areas of the face and out of other areas of the face. And you'll see that the wrinkles and crinkles develop in the expression when they weren't there in the neutral. And when Digital Ira ends up getting rendered, there's a lot of nice stuff going on in his face that we kind of just get out of the data from what was captured. When he smiles, for example, he'll get nice wrinkles and shading around his eyes that look very expressive. Everyone gets this. You don't have to be old to get wrinkles. It's just that if you're old, your wrinkles tend to stay around all the time. If you're young, they tend to develop while you get the expression and then go away once you go back to neutral. This here is showing that if you don't transition the texture, this is how much different one texture is than the other for an expression. And it really changes a lot of the face. So I'll just look a little bit at some Ira animation here, and you'll be able to notice that by corresponding these expressions with Vuvuzela, when he smiles, you'll see some great detail come up there. And you know, he's definitely got detail from multiple expressions under the hood that help make him look as good as he does for this. So that is my section of the presentation. And what I'd now like to do is invite Graham Fife to come on up here. And he's going to start talking about how Ira got his animated appearance. And we're going to switch over to his slides right here. Okay, and now we're over to Graham.
Thanks, Paul. Hi, everybody. My name is Graham Fife, and I'm going to talk to you about how we took these nice scans and then animated the character. So one of the things that we wanted to do in this project is to try to use the cameras that are available these days. It's very easy to get high-definition video on a camera. You don't need to buy expensive cameras anymore. And even the cameras that we're using for our static expression capture have a video mode. So we thought, why don't we try to use the video mode to do some performance capture? Second thing is, we don't want to put dots on anybody's face anymore. The simple fact is, with high-definition video, you can see the face's natural performance capture markers, which are called pores. But there's a couple of challenges. First of all, a high-definition video is not really enough resolution to make out the more subtle geometric properties of the facial details, like how exactly are those pores shaped, or how are fine wrinkles shaped. Although you can see these features, but you can't really make out their actual shape. And another challenge with video-based performance capture is that if you're not extremely careful about what you're doing, the performance may drift over time. And I'll talk a little bit more about what that means, but essentially, if you start at the beginning of a video and work your way towards the end, you may be accumulating error in your performance tracking unless you do something about it. So first thing we did was think about how we're going to handle the geometric detail on this video-based performance capture system. And the idea we eventually came up with was to borrow details from these static expression scans that we've done. So here's a few samples of the scans again. And we based the expressions on the facial action coding system from Ekman in the 70s. And the fundamental idea of the expressions that we're capturing is we're trying to cover the entire range of motion that the face can make. But it's not the face as a whole. It's more like if you look at a particular part of the face, like the right eye, we want to make sure that if you look at all of our scans, we've covered everything that the right eye can do. And same for the mouth. We've covered everything that the mouth can do, maybe not all the combinations, but if you look at each facial feature across all the scans, you get everything that each feature can do. So we kind of combine features across scans, and we end up taking about 30 scans to cover that to our satisfaction. So here's Ari Shapiro in our light stage again, and a couple of the scans. And our idea of borrowing the detail comes down to compositing faces together. So let's say we had some way of figuring out which parts of the face in the performance look like parts of the face in the scans. Then we'd be able to grab these nice details like the rosy cheeks when he smiles, or the crow's feet around the eyes, or also the different types of brow wrinkles you get doing different expressions. Okay, so we'll figure out how to do that. And then the other thing to work on is how do you prevent your solution for tracking from drifting over time. So if you were just to start at the beginning of your animation and somehow get your face lined up at the beginning and try to animate this face using, say, optical flip, you may find that if you just flow the face from one frame to the next, that the face will start to slide off of the video, or it may start to move around within its own UV texture space, which is equally bad. There's quite a few works on how to correct for this sort of thing. They have various occasions when it doesn't quite work out, at least for what we're doing. But we noticed that since we have all these scans, and especially since we have the Vuvuzela tool that lets us align the scans, why don't we examine how these scans match up to the video over time, and we can use them to correct the performance as we go through time. So this is a little bit like the idea of using the first frame, which is something that other people have done, or using a very common frame. But we get the advantage that we have lots of different scans that we could go back to for this correction. But there's one thing that we thought about after that. Let's look at these 3 frames of video here. All 3 of these faces look different. If you were just to do an optical flow and compare these faces, you would find that they're all, none of them really match up. The flow won't succeed across any of these pairs of faces. However, if you look at parts of the face, the left two, the mouth is very similar, and the two on the right, the eyebrows are very similar. So then we had the idea, why don't we allow our correction that we make to look at different parts of the face? So here's a visualization of what we're doing. On the left, we have a frame from performance video, and next we have an image of one of the static expression scans. This happens to be the neutral scan. And then the third image is what we get using optical flow to match the first image to the second image. And finally, on the far right, we have a match quality, which we compute based on normalized cross-correlation. And we find that the optical flow has succeeded in most of the center of the face and a little bit on the side of the jaw there. And the key idea that we've had here is we can do this kind of optical flow comparison to the static frames across the entire performance, and we can correct for drift in any region of the face that happens to match one of our scans. So if we visualize that over time, we have a video on the left, and then on the right you see a selection of the scans being optical flow warped to try to match the video. And here we see a visualization of the matching quality, where a brighter gray represents a better match. And then we also aggregate the match quality over facial regions, and this helps us decide which expressions we're going to use to composite each frame. So we had a bunch of algorithms. Let me just run that again here. Come on. We've proposed a few different algorithms for selecting these things a little bit more intelligently. But the key thing that I want you to remember is that you just need enough matches for every frame to go back to your static scans. So in case something drifts, you can correct the drift by referring back to the position in the static scans. Okay, so what do you do with all of that? You've got optical flow matching your video frames to your scans, or at least some of your frames. And then you also have optical flow in between frames, which is what you would have maybe thought to do originally anyway. So now we actually need to animate a character with this information. So what we did is we take our neutral scan and we have an artist build a very nice artist mesh, is what we call it. And this mesh is very carefully aligned to the scan, so that if we were to project this mesh back into our original camera views, it would align with the scan. Now, since we have that alignment, we can take images of the scan, which you see on the far left here. There's an image of the neutral scan. And we can take a video frame from the performance, which you see next, and we can use the optical flow vectors that we've computed and corrected using that drift correction method. And these optical flow vectors represent kind of a two-dimensional constraint, which you can project out into space, which creates these three-dimensional ray constraints. And if you have more than one camera, you can triangulate these things, and you can deform the entire face mesh from one frame to another, or from one scan to your frame. Now this is depicting taking one scan and warping it to one frame of the video. But what we actually do is we have multiple scans. So some scans might be matching the forehead, some might be matching the mouth. And also we have the previous frame and the next frame. And those again might match better in some areas than other. And we take all of these constraints together. And to ensure that we have a smooth surface on the face, we also use a Poisson constraint to try to keep the local surface shape similar from one frame to the next, or from the scan that matches your frame to the frame. And we solve all of this using a nice least squares solver thing. I don't have to worry too much about that. But what you end up with is a smooth mesh that satisfies the matches between the frame and your scans, and also matches between your frame and the previous frame and next frame. So we get results that look kind of like this. These are the artist mesh. So we have a certain number of polygons here animated to a few different performances. But there's no texture here, and there's very little geometric detail. But we can go back to our idea that we take the matching quality of the expression at every frame as it matches to the different static expressions, which we're visualizing here using different colors. And I'll try to play that one more time. So you can see when he smiles, for example, his whole face turns yellow. Let's see, can we get a play? Yes. Now what this is allowing us to do is it not only tells us which parts of the face match the expressions so that we can track, but also it lets us borrow the details that we want. We can borrow geometric detail and texture detail. I should mention another benefit of using this technique is that our face doesn't have to actually do what the original scans did. It does locally, but the overall expression of the face is free to move around and do whatever. And then we take patches of the face or individual vertices and match it back to the original scans. So even if you haven't covered the entire range of what the face does in their scans, this kind of a tracking technique can still cover basically anything that the face can do. Okay, so we take these different weights that go back to our different expression scans, and then we can use that to piece together and blend together the geometric details and also the texture details throughout an animated performance. So you see his eyebrows raising, and you get the little wrinkles in the skin, and also we get the some of the effects that Paul mentioned earlier when he's making different expressions with his face. There are some subtle shading differences and also differences in the color of the face due to the blood flow and so on. I'm going to try to get this to play one more time here. There it goes. Now we're not rendering eyes or teeth here because the way our scanning system works, we don't really capture the eyes and teeth, and we'll see with our later presenters how those were added later. So we take all of this animation information here and this texture information, and we handed that off to the geniuses at Activision R&D, and they're going to take that and make this all playback and work in real time. So with that, I'd like to hand it off to our next speaker, which is Mr. Etienne Davois. And thanks much.
All right, hello everyone. So I'm going to talk about the animation pipeline. So by that I mean everything we needed to do to get this fantastic data that we got from ICT into the runtime game engine. Of course, we wanted to stay within certain constraints, like constraints of current video game hardware and engine. So you don't need to buy like a new video card to run this stuff. So just to recap, this is the type of data that we get. You can see that the super precise, scans and animated mesh. Of course, when we're going to show this in real time, we're going to use a simplified mesh. We have here the cinematic mesh on the left and the runtime or the in-game mesh on the right. So just a little plan of what I'm going to talk about. I've separated the vertex animation, so all the low frequency stuff, and the pixel animation, so basically the texture data. Then this all goes into rendering. So let's start first with the vertex animation. So, a couple of methods to do vertex animations. In our case, what we use in digital era is linear bone skinning and a little bit of procedural animation I'm going to describe a little later. So the bone rig was like a standard 70 bone rig with linear blend skinning and 4 influences per bone, so pretty much the standard stuff. What's interesting is that this whole rig and the animation that goes with it is all derived from the data itself. So what did we derive from the data? Well, from the rig, of course, you need the actual animation of the bones are going to come from the data, and also the skinning weights are also going to come from the data. One thing that that came from an artist is just a small detail, is the initial bone position. I'm sure we could get that from the data, but we thought that it's good to have what we expect the humans to what are the important areas of the face, but for a human being, not for a machine. So we could put more bones like in areas that are more important. So how do we derive this rig from the data? Well, we're going to solve this basically in 2 different steps. We're going to solve the skinning weights first, because this is solved basically separately for each vertex, but for the duration of the animation, because of course the weights don't change for the whole rig, in fact for multiple animations. Then the second step is to optimize the bone animation, which is something that happens for every frame. We need to find the transform of the bone, and for every bone. So since these 2 things are quite different, it's much easier to solve them differently and just iterate a few times just to make sure that we converge to a single solution. Different way to do this is to use skin tracking for the bone animation, which means that the bone animation itself, including rotation and translation, will exactly come from the surface of the skin. If we do that, then we just need to optimize the skinning weight once, and it's in fact much faster. It's going to become clear in a few minutes why we need these 2 methods. So the actual solving of the skinning weights, well, basically it's just like a minimization problem. You have the standard formula for the linear blend skinning, and you're going to minimize the error, and the error is basically the distance between the vertices, the animated vertices, and the reference vertices that we get from the scans. Now, just little parenthesis, of course, if you need to know where the game vertices need to be at that frame, sometimes the mesh could be a little bit different. Like if the game mesh is just a simplified version of the scan and they share UV space, you can make the correspondence easily. But if you don't, then you need to make a match between the game mesh and the scan. Because basically we need as an input for the solver an animated game mesh. So you can do the match, for example, with the closest point, with a couple of additional heuristics, like using the normal to make sure that you match the correct point, and also diffusing on the surface. Also, in order to solve this, you need some initial values. The simplest initial values you can get for the weights is just weights from the distance of the closest bones. This is like very simple. Little bit more advanced would be to use some clustering. So you look at the data, how it moves, and you actually cluster together the areas that move together. This is what's described in the skinning mesh animations paper, which, by the way, I mean, if you want to do this stuff, this is like where you would start. But in our case, we just use distance for the bones because the optimization is going to make that converge into something good after. So when you're solving this, of course, you can just use linear least square solver, you want to add the constraint that the weights are positive, because most game engines don't really support negative weights. Simplest example of an algorithm that does this is non-negative least square. Now let's switch to the bone animation. So basically the problem with bone animation is that we're going to need to find the rigid transformation of each bone for each frame of the animation. That basically minimizes the same error that we talked before. And the simplest way to do that, and the way we actually use in Digital IRA, is to solve this separately for each bones using the vertices that they using the vertices that they affect. So, but then a problem arises because some vertices are of course shared among multiple bones. But if you really want to solve each bone separately, which is a much simpler problem, you just have to iterate a couple of times. So if you do solve for each bone separately, then the problem is very small, because at each solving you just need to do least square on the one bones and the vertices it affects for just a single frame. So, and you solve for the 6 dimensions of the transform that we need. You can use, for example, an LM solver for this. So now what happens when you do this optimization versus the surface tracking? You can actually see on here that some of the bones look like they have kind of a strange trajectory. This is basically because the solver decided that these bones would be better used as a little corrective, little correction for the animation in some areas. So it's not maybe logical if we look at the bones, but for the error metric that we decided, it makes sense. Now, is this because this is bringing back a little detail of the animation, or because it's actually representing the noise of the animation? That's something we could look at. A different way to do this is, as I mentioned earlier, to use the surface tracking. This is especially going to be important when I go back to the macro mocap pipeline a little bit later. So how do we do this surface tracking? Well, I'm going to present like the simplest way to do this. Simplest way is just to define a region around each bone. And basically, this region is going to define a set of vertices on the high-resolution mesh, which is like a point cloud of vertices. And you're going to just find the transform that brings these vertices from the neutral pole to the point cloud on that frame. And the reason we do this is that the skin is tracked, which means that for the position, it's really not a problem. But really, we need the rotation, and we need like an average rotation for the area that we are looking for. Because at that point, we don't have yet the precise skinning weight, so we don't know the precise regions. How do we, if we were using just a circle on the skin, how do we define the radius of the circle? Well, a simple way is just to use a fraction of the distance to the closest bone, which means that in areas with a lot of bones, you're going to have a bunch of small circles, and areas of less bones, I mean, the circle is going to be larger, which means that the transform is going to represent a more, an approximation of a larger area. Another thing we need for the rig is, of course, the animation of the skull and of the jaw. Now, these two things are very important because, of course, you want to attach the eyes to the skull, and you want to attach the lower teeth to the jaw. Actually, you also want to attach the upper teeth to the skull. And so how do we get these two transforms from the scans? Well, the data we get is tracked, which means we could look at just a set of points, see how they move, and get the transform. But of course, we would be getting the transformation of the skin and not of the bone, which makes a big difference, especially on the forehead. I mean, you can easily see that the skin is sliding and it's not attached to the skull. So this is where instead of just matching these few points, we can use ICP. So ICP, iterative closest point, is used to register unmatched points, which means that we are going to match actually not the points on the skin, but the overall shape of the bone that's under the skin. And just a small change that we can do to the traditional ICP algorithm is that instead of matching point cloud to point cloud, we can match point cloud to the surface of the mesh. Because if we're doing this in the game mesh, the resolution is too low. So if you don't want the vertices to just jump from one correspondence to the other, then matching to the surface itself, which means that a source point could find that its closest point is in the middle of a triangle on the target. And let me just show you the areas that we could define to do this process. So you can see the one for the skull and the one for the jaw. So basically you are going to take all these points and run this ICP between the neutral pose and the animated pose to find the transform. So since this is unmatched points, then you're going to get the transform of the shape that's under the skin. For example, for the jaw, it's going to work because the algorithm will be able to find the shape of the bone under the skin. Of course, this will not work if the actor has too much fat under the skin. All right, so now the result of all this process is that we have an animated bone rig. With the head and jaw, we have the vertex scanning weight, so like a full rig, and also the animation that goes with it, which we can just play back. Now, why did I mention marker mocap earlier? Well, when we do video games, of course, sometimes we want to go back to these markers, just because we have existing data, existing ways of working, and also we may want to capture long performances with multiple actors in a large volume. So how do we bridge all that together? This is not something we specifically needed for Digital Aura, but it's part of our whole pipeline. So the recipe to bridge these two things together is that from the scan data, we are going to do the surface tracking method that I explained earlier. From these markers, we are going to decompose the animations into shape weights, then blend the transformations of all these shapes to get the bone animation for our bone rig. I'm going to explain this in a little bit more detail. So, of course, the shapes we get, or the scans we get from a super high-resolution scan system, there are no markers there, and that's the point. Although, if we do need them, we can easily add them, because we have a track mesh. We can just add the markers or virtual markers on the neutral pose and then track them to get the markers at every shape. This is what would be on the right here. And so you have your marker mocap animation on one side. You have all these shapes made out of markers on the other side, which means you can compute the weight of each shape. So this animation frame is maybe 30% smile and 20% frown, something else. Then these values can go into blend shape animation if you would want to do that. Or you can rebuild the bone animation from that. Now, how do you decompose the animation into shapes? This is just a linear system like this. So you can see the matrix representation. A represents the marker position for all the shapes. X represents the weights. This is what we're looking for. And B would be the actual animation frame, marker animation frame for this. This is another least square problem, which again has the positive constraint, because you don't really want to have shapes that are canceling something. So you want just like positive shape, adding shapes to build your animation. You may want to put also an upper limit on the weights, just to make sure that some shapes that are maybe just subtle movement don't get like a super large weight. And you would certainly not want to just clamp these values. It's better to have a solver that actually includes the lower and the upper constraint. So, and when you get the weights for all of the shapes, which at this point could be like globally for the whole face. I mean, the way Graham described this system, he really builds an animation from small region of the face. Here, since the goal is to go back to slightly low resolution markers, you can solve this for the whole face if your shapes are well defined. Which means that after this step, you will get rotation and translation from the motion capture markers. Then you can use these exact same bone animation on the rig that we applied. Since this is all built from the same rig, you can just directly apply the animation, which means you can, build your library of animations very, very quickly. Now we'll stop at this point for a first quick Q&A, and on all the topics that we covered up to this point. Then we'll do a break, and after this we'll continue with high-frequency detail and rendering. If we have time. Do we?
Great. Yeah, we have some time for some questions, and let's take our first question here.
I had a question about, do you have any ways to capture dynamics of the face? I'm thinking of something like sticky lips, which you wouldn't get, I would imagine, in any of your static poses, but you would get in a performance. And just curious what your thoughts are on that.
Hi. Yeah, thanks. That's a good question. For those unfamiliar with the term, sticky lips refers to how the lips actually stick together because they're kind of wet. And when you open your mouth while you're speaking or whatever, if you look at it in slow motion, you can see the corners of your mouth stay closed a little bit longer than the middle because they're kind of sticking together. And that's an important thing to have in animation. So what we found is with our video-based performance capture, we get a little bit of the sticky lips effect just from the optical flow tracking, although it's not perfect. So what we would tend to do is try to build something like that into the facial rig so that after we have the tracked animation, you would have some rig controls that would automatically add the sticky lips.
Hopefully that answers the question. I put the schedule up for the second half there, so hopefully we'll break by 10:30 after questions, and then at 10:45 is when we're going to start. Etienne's going to continue with the pixel animation pipeline and getting the textures to animate as this goes through. Jorge Jimenez is going to be talking about the very nice skin shaders and eye shaders that make digital Ira look as good as he does. And then Javier is going to do the live Ira demo off of his laptop. And talk a little bit about future work, and then Hao Li will talk about the real-time capture and hair, and we'll have another chance for some questions after that. But let's take our next question here.
Hi, my name is Min Kim. Actually, I have a question about the 3D scanning on the light stage. So you combine the 3D geometry with the projector and the two different cameras, and also at the same time you acquire such a high-resolution normal. So I wonder how could you combine these two things together? Because normally such a geometry with the projectors, it contains lots of hole and it's incomplete. Yep. So I wonder how could you seamlessly combine these two things?
Okay, so I'll take the first part of the question, and then I'll turn it to Graham to talk about how these things actually get combined in a uniform framework. The first version of our light stage polarized spherical gradient illumination process did use a video projector, a single cross-polarized video projector between the stereo pair of cameras, and it would start with color fringe patterns, low frequency, kind of sine waves, out of phase, red, green, and blue, to higher frequencies. And then Alex Ma, first author on our paper about that, wrote a stereo algorithm, rectifies the images, goes across the lines, and gets a pretty good 3D shape just off of the video projector. And then separately, as a post-process, then it iteratively pushes the polygons around to emboss the surface normal information on that. We found that that worked pretty well. Sometimes it kind of missed medium frequencies of the face, so it would have good overall shape, good high frequencies, but then like a sharp edge around the nose corner might get smoothed out a little bit. And so the way that we solve for the geometry, large scale, medium scale, and fine scale is quite different today and much more unified. And Graham can mention a bit about how that works.
Yeah, hi. So if you're familiar with stereo reconstruction algorithms, they typically have two terms in some function that they're trying to optimize. One term represents how well the pixels in the different views match, but then the other term is usually just called a smoothing term that's trying to make a smooth surface. And that's kind of a generic smoothing. So what we do is we replace the generic smoothing with another term that tries to make the surface between vertices match the surface normals that we measure. So instead of generic smooth surface, we're trying to make a surface that matches these per pixel surface normals. That way we get an integrated solve that matches the pixels between the images but also matches the surface normals.
Right. So before you solve the equations, did you fix the hole in the scale with the large scale?
Do we have holes in our base mesh? And do we deal with it?
Well, the base mesh that we get is constructed with a Poisson surface reconstruction.
Oh, I see.
So, I mean, occasionally there is some amount of cleanup to do, but yeah, you'd want to have a surface that you can perform the high resolution solve on. Yeah.
So for the base mesh, you apply Poisson reconstruction before
Yes.
you apply. Thank you.
Hello, question for Paul, Sap Anderson at Autodesk. So I was fascinated by this high-resolution synthesis for the textures, and as you and I have discussed in the past, you have this issue that when you're really closed up, you have all these micro specular highlights and everything. When you take a step back, they become like an aggregate shading effect, like a glossiness. Is there some advances in the rendering of that your team has been doing to be able to basically fade between that? And yeah, I have a second question, but take that later.
That's a great question. So for the paper that we did for Eurographics 2013, we basically got 16K maps we were synthesizing up to, and they really had good information every pixel. We theoretically could have gone up to 32K maps, but the memory management for that was a little bit too challenging for us. For the renderings that you're seeing in the paper video, those were actually done using kind of brute force sampling, where the images were actually rendered very, very large and then sampled down for the video that you see with a good reconstruction operator to avoid exactly that problem that you're talking about. And you're going to hear from Activision in the second part of the course. They looked at some of our skin microgeometry data, and they're not literally using the 16K maps, but they used it as a guide for some procedural shaders that they put in. And I believe that they addressed in a pretty good way ways of getting that to not turn into either aliased chatter or smoothed out plastic looking skin. And can you guys talk about that a little bit, or is that something for Jorge?
Jorge will speak about that in the next section, so your answer will be answered soon.
Awesome. Second small question. So when you're being scanned by this machine, there's a lot of blinking lights going on. Has anybody have like an epileptic seizure during scanning?
So far not. So we actually looked at the medical literature for photosensitive epilepsy. A certain amount of people are epileptic. It's a pretty small proportion of the epileptic people who have photosensitive epilepsy. All known seizures that have been caused have been from blinking lights that are quite intense, between 9 and 20 hertz. So we keep all of our processes either slower than 9 hertz or faster than 20 hertz by quite a bit here. So we're a little bit under 9 hertz with how many images per second that we acquire with Lightstage X. We've had no problems. Some people, particularly if they have lighter colored eyes, can just think that it's too bright, and you'll get a little bit of squinting in there. We've allayed that quite a bit by having it be in a warm-up pattern all the time, so Lightstage never goes dark. In between scans, it stays at a moderate level and keeps you adjusted. And if somebody's having any trouble with the light levels, what we do is we cut the light in half, We turn the ISO up on the cameras. We get slightly noisier scans. They come out fine anyway, and it's not a problem. We've had hundreds of subjects in there, and nobody's had any real issue with it.
Okay, thank you.
Hi, I'm Morteza from Capture. I was wondering if you did any sort of radiometric calibration, and if you have any, what was the standard procedure to do the radiometric calibration?
You're talking about for the light stage itself?
Yes.
Well, we have a nice benefit that even though there's variability from LED to LED and from light source to light source, our patterns really have all the lights are on to some degree. So all those variations just average out. The other thing that's really nice about how Gram5 solves for geometry is that the variation from the different lighting patterns, which gives rise to our estimate of the surface normals, is used for high frequency detail. But it's really interpreted as an offset from the overall 3D shape stereo solve. So we don't actually need perfectly registered calibrated surface normals coming directly out of the photometric stereo algorithm. We just need relative motion of the normals in the right directions, and then Gram can get that to effectively register in to do the right things on the base geometry. The only time that we really do, well, for color calibration, we put in a color chart, X-Rite color checker. We light it evenly with light from all different directions, and then we use that to solve for an sRGB matrix that takes our diffuse maps and puts them into sRGB space, and that seems to work out reasonably well. And when we do one light at a time data from LightStage X, which wasn't a part of the Digital IRA project, but it's common when we do scans is to get an exhaustive scan, then we'll usually put a gray ball in there afterwards and then get the effect of the one light at a time on the gray ball. And then you'll see slight color variations and brightness variations from light to light. But you can divide that out by looking at the gray ball information.
Thank you.
Okay.
Hi, Alex from Weta Digital. Great work. I have a question for Activision. Why you guys choose skin blending method instead of blend shapes?
Well, for a couple of reasons. We have to work with the teams that we work with. And some of the teams want blend skinning, so that it's as simple as that. But I found it to be a very interesting approach just because you are taking dense data and you're trying to fit it to something else. So the end result wasn't necessarily blend skinning, but a proof of concept of whether you could take high density data and represent it in a different way. And with minimization, we clearly lose a little bit, but the amount of data that goes into the engine is much, much less. Now, with current generation engines, hardware, you can do blend shapes. You have no problem with blend shapes. So you could handle that. And that said, you know, some of our teams go one way and some the other. So what I would like to do, and this is more looking forward for a future, is do fitting towards a more dynamic system, something that is closer to the way your face behaves. So if you can go from blend shapes to skinning, you could go from blend shapes to this other more complex system. And
cool. Okay, cool. Thank you.
Okay. Everybody, by the way, that was Alex Ma of Ma 2007 that we mentioned a couple times before over there. So thank you, Alex, for your question.
And Alex, we have implemented your PDMs. We just have not shown them. Okay.
Hi, Darren Koska. I've got a question. So what are your thoughts on the linear blend shape method you use to solve? So you've got a linear solver there with only a few constraints. Were you happy with the solve that was coming out of that? I mean, were there any other tricks you had to use to get a good solve? I mean, or did you learn anything about strategy and the types of blend shapes to use, whether they should be sparse blend shapes, global blend shapes?
Can you tell us which solve you're referring to? Is that the tracking or the
So when you put the linear system up earlier on one of the slides, and you had a positive constraint and you had a box constraint, And so the
So
quality.
was that for the markers or for the blend shapes? I don't remember.
It was. I can't remember exactly which slide. It was the.
For the bones, because it's
You got it back?
Yeah.
Yeah.
Because I do have one here for
Yeah,
the.
yeah. So was that?
Because basically I use the non-negative least square for two things, and actually this is a super simple, but it does find the minimum that you're looking for, and for it really depends on what the shapes are. So if the shapes represent, just like the one that Graham shows, a combination of different movements of the face, then you would need to regionalize the face. Where if your shapes are already subdivided, like just representing a single movement, then you can just solve for the whole face. And it's actually much easier to do it like this because mathematically it's much more stable. And also you do have the advantage that you can see your shapes being subdivided, so which means you can tweak them, polish them, and fix them. Then you can run your solving on these whole shapes. And by the way, this is something that we have done in two places. In one case, it's just to solve the marker animation, which means that these shapes, in fact, they get transformed into marker shapes. So at that point, instead of having, 10,000 points, they're just maybe the number of markers. So it's that 80, 100, 120, or something like that. So then the problem is much more sparse. And at that point, you cannot really mask out areas of the face because the mask that you would get would have with just one markers in between, and you cannot solve one marker, you will just get noise, which means that in our case, we go for the full face because it's much more stable.
Thanks.
Hi. I was interested to see how you were deriving the rigid transformations for the skull and the jaw by using the iterative closest point. And I was curious if you had done any exploration towards furthering that approach to actually, it's interesting that you're finding the shape. A lot of times, you talked about maybe turning in, trying to fit physical simulation type systems to the data that you've acquired. And when you solve for the jaw and you solve for the skull, do you have any images of the shapes the accuracy of the shapes that you were able to get that represented that sort of average skull or mandible?
Well, actually, for the process I described, we do not directly compute the shape of the skull. What we use, in fact, is the shape of the skin that is over. But we did some research where we would compute the minimum surface. So, in fact, you would solve for the surface that is the closer to the center of the skull for the entire animation. And of course, at that point, it may move. So you need to solve the two things at the same time so that you find the minimum position and it's transformed at the same time. So then you would get some kind of representation of what the bone is. But we did this as a research to push this further because there are limits to the system.
It would be very interesting to see if you could derive teeth shapes and then turn that into a collision model. And
exactly.
think about the retargetability of that. It would be really amazing because then you could get really realistic physical simulation on a wide variety of heads. And it wouldn't just be all capture from that point. Thank you.
Yeah, thank you.
Yeah. There's going to be an interesting paper in the SIGGRAPH Papers session from Disney Research about fitting a anatomical skull model to facial scans so that you can stabilize the position of a face over a different scan sequence. And that might be another way to try to get the models of teeth in the right place for the kind of simulations you're interested in.
And let me add something to that. To the answer of Alex Ma, that minimum surface model, that is what we were actually trying to fit first. So we were trying to find that minimum surface model, then find the dynamics in between, and then create a system. But our games are now going to be driven like that. That's be super interesting research. I think we need a little bit more computation to be able to drive that.
Okay. And final question before the break.
Yeah, just real quick, Spencer Alexander from Sucker Punch. I was just curious about your light stage, Paul. You have the lights in all directions. Are the ones that are on the backside of the hemisphere, are those specifically, I guess, would that just be for the Fresnel, or how is that?
Good question. Well, we use the light stage for a bunch of different purposes. So high-resolution facial scanning is one of the things. Another one is to do one light at a time and basically read out BRDFs. We do it for capturing material samples as well. We also do it for lighting reproduction, which is a form of like real-world image-based lighting, where we've got color LEDs all around your actor. You just want to light them the right way so that they'll composite correctly into a virtual scene. This was a big technique that was used in the movie Gravity, for example, using some systems that they built for that. And for a lot of those processes, you really need lights to go all the way around. We recently did a facial scan that had to be done in a mobile unit with a project that took place on the East Coast with the Smithsonian Institution. And for that, we had to work under somewhat strange circumstances. Couldn't really bring the entire spherical light stage, so we actually were able to get one of these polarized gradient illumination scans pretty darn well ear to ear with just the front 180 degrees of a light stage. So for the facial scanning, yeah, you don't absolutely need to have the full sphere, but then you have to put some correction factors in because you'll get darkening of the diffuse maps as you get toward the edges, and for that project I alluded to, Graham Fife figured out ways to do the correction. So it's nice to have the full sphere. It's necessary for some of the light stage processes, but if you just want to get a good facial scan, the real key is you need to observe a specular highlight off of the skin, off of every one of the surface normals that you want to get a good spec map and a good specular surface normal off of.
And for the Fresnel, is that particular?
Yeah, so it's nice to be able to see the Fresnel, but basically the way that the different scans are merged together, you're mostly using the data that faced any particular camera. So the Fresnel does start to edge in toward the edges of where you're doing the matching, but when you finally do the final texture blending, you're probably stepping around the Fresnel reflections of any particular view as it gets into your final flattened 4K map.
Yeah, makes sense. Great, thanks.
Okay, great. Well, thank you for all of those great questions. It's 10:34 right now. We're going to resume again at 10:45. I'll put the schedule on here, and we're going to be hearing about pixel animation, skin shading, eye shading. That's very important for Ira, the live demo, and future direction. So I hope to see you back here in 10 minutes. Thank you very much.
All right, so let's resume this. So I'm going to continue the second part of my talk with the pixel animation. So representing the high frequency data. So again, on our side, we really wanted to do something super lightweight so that it can run in game engines, that have other things to do than to display just a single head, like they're computing AI and the environment and so on. So the lightest way we found to represent the most detail in the maps is to use just 3 maps blended. So 3 normal maps, 3 diffuse maps, 3 displacement maps. Of course, it means you have the compressed, neutral, and stretch maps. Now these maps we created them by compositing the areas of maximum stress in all the shapes that we have, which means that since we have just 3 maps, some of them, they contain detail from multiple maps. So how do we define this surface stress? Because we're going to use that value both to create these maps and to display them at runtime. So basically, this stress is the amount of stretch and compression of the skin. Of course, when you're computing that value, the scale at which you are doing it is super important, because if you think about it, a piece of skin, at a certain scale, it may be folding, but at a different scale, a larger scale, you can imagine that it's really just compressing because and if you look at the distance of the vertices on the game mesh, it's really stretch and compression that's happening, even if in between these vertices, it's really folding. So So one of the simplest way to compute this value is to take the ratio of the length of the edges that connect each vertex, which means you're going to get one value per vertex, and you can look at all the edges connected to this vertex. You divide by that same value on the neutral pose or on the rest pose. So one is going to be same as a neutral, and you have a value for compressed and for stretch. You can see the result, an example of the result here. When the eyebrows are raised, the forehead, of course, compresses where the area above the eyes will stretch. Different way to do this is, and perhaps a more stable and more smooth way to do it, is the standard deviation of the position of two levels of connected vertices. This is what's done in the polynomial displacement map paper. But on the runtime part that we are going to show for digital IRA, we used the edge length approach. And of course, this value, you can also project it on the local UV space. That way, you are going to be able to represent two dimensions of stress. So, for example, one piece of skin could be compressing in one direction and stretching in the other direction. If you have a single value, these will cancel out and you will get no stress. But if you do that in 2 dimensions, it means that you are going to have 2 times, of course, the number of maps to blend. Now, as I said, in the runtime demo that we are going to show, even though we research all these other methods, this is the edge length method that's going to be used. But we also have a way to bake this stress value offline, which means that we look at the animation offline, we compute the stress, which could be from any method to compute it. Then we bake this and we store it with the animation. This has the advantage that you can double check your stress before playing back the animation. You can even tweak it. But if you store all the values, it means you're going to store one stress value per vertex per frame of the animation. So that's too much data. So you need to compress that. You can do that with reduced basis. In our case, we use as this basis the regions that come from the linear skinning, because these represent really partitioning of the face or small regions of the face, and that data is always already available in the engine or in the tools because we need to animate from these values, which means that you are going to go from one value of stress per vertex per frame to one value of stress per bone. So in fact, you're just going to add one channel on each bone. This is going to be the stress for the region affected by this bone. And at runtime, it's very easy to blend this. And another advantage of doing it this way is that, of course, the stress is going to be a little more smooth because these source regions, the skinning region, they are already smooth because they represent the movement, and they already define the boundaries, the natural boundaries of the movement of the skin. So if you have any artifact or anything, it's going to follow the natural shape, the natural movement of the skin. Now, you may want also to keep more details. I mean, 3 maps is really not a lot. I'm sure we are leaving a lot of detail, losing some detail. 2 ways here quickly to keep more detail. I mentioned it, the polynomial displacement map, where your data from your textures would be transformed into polynomials, which means that each value becomes a function of the stress. So you just need to store the coefficients of this, and at runtime, if you want to just evaluate this polynomial from the current stress value, then you get your value back. For example, your displacement value. Another way to do this is to keep a lot more maps. For example, keeping 1 map per shape would be the ultimate. And if you want to reduce the size of all these maps that are perfectly aligned, you can run PCA and just keep the largest components of these maps. Those are just two different ways to keep more detail. Now let's switch to my favorite part. It's just a little bit of procedural animation that we need to add on top of the bone animation. Because bone animation cannot represent everything. It cannot represent, for example, this sliding movement. You can see that the eyelids are being pushed by the bump of the cornea. With bones, this is hard to do, and we decided to make a very lightweight rig out of bones, but these type of little corrections can improve the result. So how did we do this procedural animation? Well, basically, this is done in the domain shader, so at the same on each vertices after the subdivision. Basically, each vertex is going to be offset from the center of the eyeball by a certain value, and this value is a function of the angle from the center of the eye. Which means if you look at this little graph, if the vertex would happen to be exactly in the front of the iris, it would be displaced by a large amount because it is exactly where you have the bump. And as you move away from the center, then you can see that the bump diminishes, and then it's zero in the part of the eyeball that is perfectly spherical, or a good approximation of a sphere. Then there is a second bump around 90 degrees. This is actually where you have the muscles attached to the eyeball. You can make the exercise with a friend later. If someone looks to the left, for example, you can see that the skin on the right of the eye is going to have a little bump forward. This is because all these muscles that come from the back of the eyeball are pushing on this skin. And by doing this, both of these effects are represented, and this is very simple to evaluate at runtime. All right, so that's it for the animation part and the pixel animation. Now I will give the mic to Jorge Jimenez. He will render all this data. Thank you.
Hi, my name is Jorge Jimenez, and my part of the course will be rendering, and as you will see, is all about the details and how a collection of really small things can be crucial for bringing characters to life. Something that I learned all these years working with faces is that each character rendering feature counts, even if it doesn't seem to make sense when used individually. So let me present Lauren, one of our test characters, which is rendered at 180 frames per second. And this is important for us because we need the rendering not only to produce realistic results, but also to be really fast. Because in games, we only have approximately 16 milliseconds. So that is, as you can imagine, not that much for doing this. So there are many things that are important for character rendering. So, for example, the modeling, the shadows, the eyelashes, the specular reflections, the occlusion, the skin, the post-effects, and, of course, the eyes, which can be described as windows to the soul. They are, in my opinion, of extreme importance for showing emotions. Notice that in this real-time image, to a certain degree, we manage to maintain realism, even that close to the eye. So here you have another shot where you can see the light transport happening in the eyes, which includes light refraction and the smooth color shadows on the top of the eye produced by subsurface scattering. In this one, you can see the power the eyes can have for showing emotion, and also the soft specular reflection of all the skin and the importance of depth of field in portrait shots. This other one shows how soft lighting can further reduce the specularity of a face and how important the eyes can be in a composition. In this one, you can see the diffuse lighting together with strong specular bumps and how film grain can add realism to a character shot. I would like to remark that you will be losing a lot of details in the projector because they usually don't do justice to character shots. So maybe I will be talking about things that you cannot actually see on the projector, but you could actually tell if you were looking at the monitor. And there is much to say about this one. You can notice the strong features of the skin and at the same time how smooth it looks like. Achieving this is for me one of the biggest challenges that we faced. Also, you can see the reflection on the eyes and how they reveal how wet they are, which can help to convey character emotional state. And last but not least, you cannot tell in the picture very well, but you can see how the light is traveling through the nose of the character and how the light is refracting in the eyes and the subtle yet noticeable poor detail in the face. So I'm going to show you some images turning on and off everything that we do for character rendering. So this is with everything enabled and this is disabled. So I will go back again. And you can see how the character turns into a doll when you turn everything off. And they are especially important the closer you are to the character. In this one, you can see the refraction in the eyes and the specular details. So in my opinion, our technology has the potential to take a current generation character and bring it to the next generation live. So what's going on? For me, it is that in the real world, nothing is perfect. And too perfect renderings tend to look unrealistic. And that's possibly the fastest road to the uncanny valley. The level of detail of characters has been increased in the past few years in games. Now there are many games that include incredibly beautiful and detailed faces, but unfortunately, if we don't raise the technology to the same level, this is what you will get again. So this part of the presentation is composed of two parts. First will be the skin, and then it will be the eyes. So for us, the skin rendering has two main components that you need to model properly. First, the light reflects off the oily layer of the skin. And second, the remaining light enters into the skin and then scatters, which is a phenomenon called subsurface scattering. So I will start with the specular reflections and what we did for improving that. So what's the problem with the specular? For us is that it looks like plastic. So how we can break this appearance and turn it into something more like this? Again, it's the same because I think the projector is not making justice to this. You will need to be closer probably to see the difference, but it's actually really noticeable when you are closest to the image. So we begin with the production-proven Black Ops 2 specular model as foundation, which is physically based, and that means that it ensures accurate results with no manual tweaks. So using this model, we try to mimic the results from a state-of-the-art report from the ICT, which Paul explained before, where they describe a really accurate skin capture system. But the issue that we have with this is that we unfortunately cannot use 16K maps for our characters. And also we have some time constraints for developing this. So we try to figure out what we can do for trying to simplify what they did in a way that actually resembles the final result. So for me, one of the key contributions of this paper is that it reveals the importance of having two specular lobes for rendering skin. They obtain the lobe parameters using fitting techniques, but we managed to get similar results by actually visually adjusting them. So here you have the fit that they obtain, and this is what we are doing. You can see that it's actually pretty similar. And this is the difference from using one lobe and using two. You can see there and here some additional specular glints that I think are important for conveying that the face is actually oily. So digging further into the details of this work, and this is where the 16K map didn't fit into our engines, is that you can see that they don't only fit the BRDF using capture microgeometry, but they also render with that. So you can notice how the microstructure pattern breaks the synthetic appearance of the reflections. And we again wonder if we could try to find something plausible in real time and get the same result. So if you look closely to the microstructure distortions, you will notice that they look pretty much sinusoidal. So we thought, why not trying to perturb the original base map, which is usually 2K in our case, with a tiled sinusoidal noise. And we found this simple approach to yield really good results. So this is what they obtain, and this is our simplified approach, which is actually worse than theirs, but for us it's probably good enough, and it's actually improving the look of faces in a game. So here we have a render with two lobes, and here with two lobes and the microgeometry noise. You can see how it is actually breaking the orange style bumps on the face into something more organic. So something important related with this is with microgeometry is the roughness and the specular aliasing that a tile noise can generate. So the roughness of a material depends on how flat or randomly oriented are its microfacets, as you can see in this image. So a glossy material, like the one on the top, will have a flat surface at microscopic level, which will lead to sharp reflections. But on the other side, a rougher material will have a more random distribution of facets, as shown on the bottom, which will lead to blurrier reflections. And this is where I think that things get interesting, and is that our microgeometry is small enough to be considered microfacets when you are really far away from the skin. So this means that our tiled microstructure normal map can convert to roughness when we see the head from far away. Just to show this with an example, here we have the normal MIP maps, and as you can see, they actually flatten with distance, so this part is completely flat. Then we can convert this normal map into a gloss map by estimating normal variance, and we obtain this result. And then what we get with this is that we are obtaining a physically plausible glossiness instead of relying on paint maps, which sometimes have no real meaning from a physical-based rendering standpoint. You can see many times using color maps and tweak as roughness, which, if you think about that, is not the right thing to do. So if you notice in this image, you can see how the gloss noise, unlike the normal map one, is present even when far away from the model. So here, the normal map was actually flat, but you can tell the noise. And what this means is that the normal map won't add too much when the face is far away, but the tile gloss will add sparkles, and this will add more viability, more realism to the face. It will look much less flat than what it would look like if you were only considering the regular bump. So we wanted to have still some control on the gloss on the face, basically to make some areas be more glossy than others, like for example the nose or this other part. So we will have now two sources of glossiness, which is the artist-author gloss map and the gloss values obtained from the tile noise. So for combining them, you need to store the noise variance alongside with the normals, and then you combine them in runtime. But I will refer you to Stephen Hill and Dan Baker presentation for more details about how to actually do this. And as a final comment on gloss maps authoring, our recommendation is to author low-frequency details on the gloss map, which is something that artists can really understand really well. I mean, everybody can actually tell that the nose should be more gloss than, for example, the cheek. And then add the micro details, which is the hard part using tile, bump, and gloss. So I would like to also highlight how hard authoring gloss can be, because it depends a lot on lighting setup, and this is something that doesn't happen in film, because in film you many times can actually tweak something for the scene, but for us it's different because we run in real time. You can move around. The lighting can change depending on where you are. So this degree of freedom means that everything needs to be consistent under all lighting situation and all conditions, which makes this authoring of maps much harder than what can be where you can actually tell where the camera will be and what the lighting condition will be. So, for example, the size of the light and its distance is something that you need to take into account. So here you have a point light source, and you have here a bigger area light, and you can see how the specular lights, the specular reflections have softened. So it's not a change on gloss, so use the area of the light that changes. So we like to think of gloss and the size of the light as two sides of the same coin, as they both blur and sharpen the specular highlights. And what this means is that if you properly author, for example, for this, it may be the case that you are making things in, it will not look properly when you change, for example, the size of the light. Or, for example, it's the same for the Light Pro. So, for example, in here you have a harsh Pro lighting setup, and here a softer one, and you can tell that the same happened. Here they are sharper, and here they are more soft. So this makes authoring gloss challenging to artists, because they can maybe make it really sharp here because they want the speculars to pop, but then here they will be completely crazy highlights. So that's something to take into account when trying to properly author gloss, and is that the environment actually affects how they will look like in the end. So the next topic are human pores. So this beautiful image is an scanning electron micrograph of a human pore. You can notice there that there is a lot of occlusion happening, and you may be thinking that this is completely irrelevant for rendering and without the same, but I think we were wrong. So if we compare a render with a photograph, you can actually tell that we are getting specular reflections inside of the pores, which in general that's not something that will happen in reality because there is a hole there. So to solve this, we are basically using a cavity map. And here you have a comparison between not using a cavity occlusion map and using it. So you can see how the reflections inside of the pores actually disappear, which adds more imperfections to the skin reflection and make it more believable. And this helps to add occlusion to the pores, which is important for ambient lighting, as you can see in this image, hopefully. I will also recommend you to download the slides later on and see everything full screen, and you will probably better understand what I'm trying to explain. So a problem with the cavity maps are that it's not as simple, because if we turn the light to the side, we are in trouble. This part in here is completely hard and naturally contrasted. So basically, in this image, we are using the cavity map as a specular occlusion factor, effectively multiplying the specular by the cavity map. But the problem is that from the side, you don't see the holes. So you should not be doing this when looking at the face, at the surface from a glazing angle. So for this, we basically remove the cavity at glazing angles, which can be for which there is a trick that we use for efficiency, for performance. That is, instead of multiplying the cavity map to the whole specular contribution, what we do is to multiply the reflectance inside of the Fresnel function, which will make this properly behave without any more additional math than a single multiply, which, as I mentioned before, the number of instructions is something that we are always keeping in mind, because there is not much you can do in 16 milliseconds. So this is not good, because it looks really hard in this area, but this is a little bit better and more smoother. So now I have finished with the specular reflections, and I will dive into subsurface scattering, which is, in my opinion, one of the most important parts for rendering realistic faces. Without it, rendering hard or wrinkled faces like this one is extremely difficult. So this is on and this is off. So here we have another comparison using a harsh lighting setup. And you can notice the importance of subsurface scattering, especially on the gradients here and the shadows, and also in the shading in the nose. So a lot of you will already know this, but I would like to give it a quick review anyway. So when rendering skin using conventional techniques, we make the assumption that the light scatters at the surface. So it basically exits at the same point where it enters. And this model, which is called a BRDF, works really well for simple materials like stone or plastic. However, when rendering complex materials like complex translucent materials like skin, we have to use the VSS RDF model, where light penetrates the surface, travel beneath the object, and then exits at adjacent points around the incident point, which basically means blurring the lighting. But you can notice that the BRDF is a 4-dimensional function, while the VSS RDF is an 8-dimensional one, which is obviously very costly. So since 8 dimensions sounds like too many dimensions, the problem is usually simplified by using the diffusion approximation, which basically reduces the description to a single parameter, which is the distance to the incident point. So you can see here in this graph, where you have the distance on the x and the intensity on the y, how the light actually decays with distance and how it decays differently for each channel. So for example, the red channel, the red color will actually travel more beneath the object and will look more blurred than what the blue colors will be. So applying a diffusion profile consists on blurring this irradiance texture with a 2-dimensional convolution, which unfortunately is really expensive. So another problem that this approach has is that this map needs to be generated each frame, as it contains lighting information, and you cannot bake this offline. So back in 2007, the work of Eugene Dion enabled to apply this expensive 2-dimensional convolution in real time. The key idea of this work is to approximate a profile by a sum of Gaussians, which is possible given its similarity. This has a really important advantage, and is that Gaussians are a symmetrical separable function. And this means that we can replace a two-dimensional Gaussian by two one-dimensional Gaussians that will be performed really, really quickly. However, this approach has two problems that made the technique to not be completely practical in games. So the first issue is that blurring in texture space is costly. So for addressing this issue, what we did is to render in the lighting. So instead of rendering the lighting into a map and then blurring that, what we do is to basically directly blur screen pixels, which kind of approximates doing that in texture space in most of the cases. So the other problem is that even if it was really fast and real time, six Gaussians are still too many and more than what you can probably afford in a game. So for this, we tried to figure out if there was a way for having something that looks similarly but not the same, exactly the same. So we found a separable convolution that approximated the original non-separable one. So this means that instead of having 12 passes, we just need to apply 2, which will be many times faster. For more details, I will just refer you to the previous work. So I will now be switching to the next big topic, which is eye rendering. I would like to start with some shots that highlight the importance of properly rendering the eyes. Here in this shot, you can tell the caustics in the eye in this area here, and also the refraction and the correct shadowing on the eyes edges, the wetness on the eyelids, and how important these features are for the eyes to be actually integrated into the face. Here you have another shot where refraction is more prominent. So a lot of you will probably already know this, but let me quickly review the most important parts of the eye used for the people that have forgotten. So the sclera is the white part of the eye, the iris is the color part, and the pupil is the black part inside of the iris. And then we have the cornea, which is a thin transparent layer that covers all these elements and the origin of all the refraction phenomena which happens in the eye. So this is the first feature I want to talk about, which are the reflections on the eyeball, which are probably one of the most important things that you have to take into account. Without them, you are actually killing the character. We found that only including direct light reflections are usually not enough for most lighting configurations. So we basically include regular environment map reflections, which allows to obtain this result. But the issue is that it looks actually like a mirror. So the challenge is in how to turn this mirror-like appearance into something that feels more organic and wet. So looking at real eyes, we realize that you can see strong sign-like distortions caused by low-frequency changes in the normals of the fluid surface. They only happen on the sclera, whereas the reflections on the cornea are perfectly sharp, which actually makes sense because otherwise we will be probably be looking at the world in a distorted way. So we created a high map for using sign functions and then generated a normal map from that. And you can actually tell that this is the same noise that we use for the screen microgeometry. So this little change improved the quality of the reflection significantly, but we are still halfway done. So we try to discover the visual clues that can cause an eye to look wet. So for that, we shoot eyes in different situations. First, with the eye in a normal condition. Then, after blowing air into the eye for about 1 minute, which will make it dry. And then, just after you stop blowing air, it will quickly become wet. And then we use a checkerboard for having predictable reflections and actually be able to tell how the reflections are being distorted. And then this is what we obtain. And the main difference we found between a dry and a wet eye is that some waves with lower frequency and higher amplitude starts to appear. For this, we created a completely empirical shader that combines low and high frequency details depending on wetness, and I will refer you to the notes if you are interested on the details. So here you have some renderings. This is for low wetness, this is for medium, and this is for high. And other visual cue that we found to be important are the specular lines in the eyelids. So for doing this, what we did is to create different geometries for simulating different wetness conditions, and then we used blend shape them. So here you have a shot without the wetness geometry, and here you have other with it. So you can see here that an specular line appears in this area and also covering the caruncle, which makes the eye to actually feel wet, in my opinion. And here you have another shot without, and this is with. I think we try to figure out what's going on with the eyes when somebody. I am sure that you many times have seen people that suddenly have brighter eyes when they are extremely happy, extremely sad, or even jealous. We try to figure out the reason, and it's not that obvious. And actually, from what we research, the reason for the eyes to have this sparkle in the eye, the reason for that is still not completely understood. So now we have better looking reflections, but what happens with the eyelids and the eyelashes? They should be blocking the environment, as you can see here. This area is completely on darkness, but they don't. And then this looks like more like the eyes look like it's actually sitting on top of the face instead of being inside of that. So they are, I think, important for making it feel properly in the surroundings of the skin. So for this, we try to see the fastest way to solve this issue in real time. So we simply use a bake reflection occlusion map, and then we apply a little bit of parallax depending on the view situation, so that the occlusion doesn't look like a sticker on top of the eye, but actually reacts to the view camera movements. Then something that we realized later is that occluding the environment is not enough in some scenarios. So, for example, here you can see how the nose is being reflected in the eye, and here you can tell the same thing in this area here. So we also explore the idea of using screen space reflections for the eyes as an alternative to the vague reflection occlusion approach. So the goal for this is not only for having occlusion, but also for actually reflecting nearby objects and the light intensity that they have, because we have the intuition that this could make the eyes feel even more integrated into the skin. So we found this to add more coherency to the lighting of the eyes with respect to the face. So this is off and this is on. Probably hard to tell in the slides, but here in this area, you can see how the nose and how the caruncle is being reflected on the eyes, and is helping to conveying that the eyes are wet. So the next feature I want to show is biorefraction, which probably is the most important feature you need to include in an eye shader to look realistic. Because this makes the iris to look like a really three-dimensional structure instead of being something flat, especially when you look at that from the side. If you fail to take this effect into account, it leads to a cow-like stare like this. So this is on and this is off. Probably you cannot tell too much, but the pupil here is actually being pushed outwards if you don't take a view refraction into account, which which creates a really weird stare on characters. Something that we want to point out is that for performance, we render everything in a single mesh using 2 layers. One is for the sclera and the other is for the iris, and then we smoothly blend them together. So basically, we replicate the lighting twice for both of them. So on the right, on the left, you can see the 2 layers blended, and on the right, you can see them without the blending. And I am pointing this out because doing this 2-layer approach enables the eye to look more three-dimensional. So, for example, in this case, you can see the limbal ring, which is the dark area surrounding the eyes, which is present in this image, but it is not on this one. It disappears when you move the camera to the side, which is something that happens in real world, which gives a more three-dimensional appearance to the eyes. And I encourage you to try this with college that has light eyes, because you will probably perfectly see this phenomenon. So we have got reflections and view refraction, but light also refracts when it travels through the cornea. So here you can notice this shadowing effect on the right, which comes from refraction and change from refraction, which changes the light direction in such a way that this area is completely unreachable from this specific light angle. And so this is the starting point, and here we don't have light refraction, which leads to a really flat and natural appearance. And this is with light refraction, where you can actually tell how this shadowing in the eyes starts to appear on the opposite side to the light, which is something that we found to be interesting, because you can see that usually when you light something from the right, you will get the lighting, the shading will be bright in this area and dark in the other, but it's not the case for the eyes, it's the opposite. And the reason for that is the light refraction. And then if you increase the light strength and you move the light to a more glazing angle, you can see how caustics starts to appear in the eye. And this is again without this feature. To try to help to explain why this happens, you can see here this graph where you have green rays coming from light on the left, and you can see how the angle changes on the cornea because of refraction, and then they turn into the red ones. So if you follow the last ray here until the cornea and then until the iris, you will see that this area is not receiving any lighting, which is the reason for shadows to appear there. So we work on the idea of pre-computing irradiance for all possible incoming angles, because as you can imagine, refraction is not something, light refraction is not something you can calculate in real time, which is an idea which is already explored in previous work. Then the results are stored into a three-dimensional texture which encodes for, in each slide, the irradiance of the iris for a specific inclination angle. So as final comments, I would like to remark that our technology runs at 180 frames per second on a GeForce 680, which means that it's running much faster than what you need in a game. And then I would like to remark that when the face is covering most of the screen, it actually makes sense to give it more attention and more horsepower to actually render that properly, given the importance it has for conveying emotions to the gamers. And also, if you cannot afford that, other possibilities simply pre-recording their cinematics at 1080, because it actually makes a really big difference. So this presentation is being displayed right now at 720, and this is probably one of the few cases where 1080 actually makes a really huge difference. And you can see that on Blu-rays, where faces looks much better on 1080 than 720. So I would like to finally remark that for character rendering, its detail counts, even if it appears to be subtle difference when considered individually. But when you combine all of them, I think that everything starts to make sense. I also think that perfection is the enemy of photorealism, and overcoming that is the most important goal for crafting believable images. And finally, we believe that overcoming the uncanny valley and the strong revulsion that it produces will enable to increase empathy with the characters and will hopefully help storytellers to create stronger links with the players and more deeply reach their feelings. So this finishes my part, and now Javier will show a real-time demo where we can see what happens with pixels from the beginning to the end of the rendering pipeline.
Change the screen. One moment. Duplicate this display, supply. Now I'm saying keep changes. I'm going to show this at 1080p. As Jorge just reminded me that it's very important. And I'm sorry, I'm starting from Visual Studio because I want to show you that this is real. This guy, actually, I want one comment about this guy. He's one of our colleagues, Bernardo Antoniazzi, and we have scanned him in all sorts of different ways, including we made him grow a 4 months beard and we made him shave it to see if we could track it. The camera shook, and we have to wait 4 more months. Another thing that we actually have from this guy is we have the back of the head. We actually did a light stage scan of the back of the head. I remember Paul was mentioning that most characters were scanned ear to ear. Well, this guy, we actually have back of the head. We also made him shave. So if you see this particular back of the head configuration, you know it's Bernardo because it's appearing in all our game characters. And as well as some of ICTs, I think. Digital Ira had the back of Bernardo's head. So I will actually do a little live demo, and I wanted to remark on one thing that Jorge just said, that for character rendering, every detail counts, and I will expand that. It's not just for character rendering, it's for approaching the uncanny valley, for animacy, for realizing that this is a human that you have in front of you and not a bunch of pixels. That means every single detail in the rendering, but every single detail in the animation, every little twitch. And we are there somewhere, but and we tend to accept animations that start losing these things because this is what we have. But if we want to get to crossing the uncanny valley, we do have to get there. So I will briefly go through Jorge's presentation with a slider, so live. This is just a normal map. It's great. This is actually captured with a light stage. This is, I would say, the video games we used to be accustomed to a few years ago. It has diffuse and specular, right? So diffuse and specular. It is pretty ugly. Now, and you can really tell that it's ugly when you actually make a very hard light conditions. Now, this is the first step, I think, the great breakthrough that Jorge came through. He says, well, can we make subsurface scattering applicable to this? So, and you'll notice, like, as you put subsurface scattering, all of a sudden this is human. It goes from a piece of stone to something human. I mean, this isn't perfect yet, but it's much more like something we like to see. Some people say that, well, you should just design your game for the lighting condition and then stick to it. But, that is kind of a self-defeating argument, in my opinion, because if we want to recreate our environment, we have to be able to get direct lighting, studio lighting, indirect lighting, and whatever else that you might want to throw at it. So I think this project, in this project, I think that we try to approach it from multiple different perspectives that way. I'm going to put a little bit of back of ambient light. Then the next step in here in this slider is it's very subtle, but it's the specular. Sorry, the specular, the microgeometry and the high detail specular, the dual lobe and the microgeometry. I think it goes in here. In some characters, you see it better than others, but it is very, very important, and this is also very important for direct light. So. On full sunlight, if you don't have a good specular response, you can tell that you're looking at a piece of ham and not a human skin that has a lot of details and oil attached to it, and dirt. Actually, this is at the level that we stop working. We have no dirt in here, and it troubles me. And Jorge is laughing, but it does make a difference in creating the animacy of a face. These faces are still a little bit too clean. And again, I'm going to quote him in saying that what we want to make sure is that the perfections are taken away in order to feel like it's integrated into our environment. On the next step, it's some baked lighting. You see there's baked lighting to hide sorry, I think here you included baked AO and bent normals, right? On this one, yeah. So, it's right. So it works. Thank you. Right. Yeah, exactly. So this is an effect for ambient lighting. So you have to be able to handle ambient lighting well. If you have a lot of ambient lighting and you don't have some form of baked lighting, then everything just loses ground again. And then finally is the iris. I'll show this same thing in another character with bigger eyes. And iris, eye wetness, and at the last level is the effects, the depths of field, the film grain. This is what integrates the character. This can help integrate the character from a pure CG image into a photograph. And if the depth of field is done mathematically accurate, it will fit correctly. And I think that we have done it mathematically accurate. Now, all these effects that Jorge have been working on are all in, except for the eyes, correct me if I'm wrong, except for the eyes, they are all in screen space, right? Just about. So this is probably the main reason why this can run so light. This is just 2D effects on the screen that are highly optimized. So I'm going to go now briefly to our digital Ira, and it's Ari in the room. Hi, Ari. I'm gonna play your favorite line. So. Make sure and we actually brought some yogurt parfait for yourself. But as soon as it loads, it just takes a little bit to load. Okay, so this is Ira. Oh, and there's one more step that I'm forgetting, is that Ira was bold. Well, it really no longer is. So we just grew hair. And we don't have slides to talk about this hair, but and so I'm sure there will come at some point. But there's something interesting that happened. We actually took the hair from TressFX and optimized it to the point that it has no effect on performance that I can tell in my computer. I'm running here on, by the way, not a GeForce. I'm running a Quadro, a 3-year-old Quadro laptop, so that it runs. At all, it's great, and I think I'm here about 30 frames a second. So here's digital Ira, and I'm going to animate you. Let me see in your.
I ordered a yogurt parfait, and the whole parfait was fruit, frozen fruit. There was no yogurt. It's supposed to be half fruit and half yogurt, but the whole thing was frozen fruit.
Yeah, so I'm going to, okay. So this is a little infamous line, which we didn't realize that it was going to be considered to be so funny. But that's what it is. So here, I just turned it off because I want to show you a couple things that are happening. Etienne earlier was talking about blending stress, the difference between blending stress live and blending stress, blending normal maps. And yes, we're only using two high-resolution normal maps, two stress normal maps, one for compression and one for stretch. And we can actually preview the two different results with the to see what actually happens on the skin as the skin tenses and compresses. Again, as Etienne said, this can be improved, and I think this is this is where we are at right now. We have to be able to precisely reproduce what Ira can do with his face, with his wrinkles, because we have all that data from the light stage. So this is the baked stress, and I'll show you the dynamic one, which was used for some of an older games, which is much more noisy because it is looking directly at whether each polygon compresses or stretches. So you got very high breaks, with I think green being stretching and red being compression. So we're going towards this, but I think plenty of work is needed in this area. Where else am I going to show? Okay, so I'm going to switch to another of our characters, which is Lauren. Where's my animation here? Animation. And I will do Lauren. Where is Lauren? There's Lauren. So, no, it's okay. It's fine. I just have the stress preview in here. So she is not stressed at all because she's static. So what do I want to show you about Lauren? Now if I see if I can recall my presets. Nope, that's not it. No. All right, so let's just go to one of these. I just want to show Lauren, unlike Ira and Bernardo, Lauren was scanned by, I forget the name of was it Lee Perry Smith? I forget his sorry? Infinite Realities. And then we had an artist in the Czech Republic paint, Zbigniew Kisela, paint the pores, and he did a phenomenal job at getting to the very close to the nitty-gritty. But so this is our Lauren. She has beautiful eyes, so it's great to demonstrate what Bernardo what Jorge was talking about, as well as what Etienne was talking about eyes. The eyelid bulge. Let me actually get it nice and big. Okay, stop. And I'm gonna change the camera to a slightly different f-stop, so I'm not so out of focus. I like to be able to do that. Okay, so there I am. So if I grab the eye, this is live, and it adds to I think nice moments. It's super cheap, and I don't know why nobody has implemented this yet. They should, because it's really a gimmick, but I like it. So on light refraction and the limbus, I'm just going to go to the eye, limbus, make it really extra large. And then you notice there's no limbus here. Something else that's happening is because the light is hitting it right from the front. But if I take this light and throw it to the side, you'll start to see the limbus appear, right? So all these phenomenons are attached. So as the limbus appears, and I don't always, as the limbus appears, you can also start seeing the light refraction hitting on the side of the eyes. And with this eye, I want to also show you what I was doing before on the debug for the eyes, because this you can see very well why this is important. Camera, if I can see, I'll put that in there. So this is no refraction. This is sorry. Yes, no refraction on the eye, and this is with refraction on the eye. So you can really tell that this is not a character that you want to deal with really in life. I mean, it's a little bit scary. She has an implant. She doesn't. And just lastly, again, Jorge talked about the importance of animacy, the eyes in animacy, in recognizing what is good, what is human, what it isn't. But it's also very nice to see what you can do with just a couple little effects on the eyes. And I'm simply going to take the pupil, I'm going to expand it a little bit, I'm going to add a little redness, and I'm going to make it a little wetter. Where's the wetness? Wetness. I'm going to make it a little wetness. And just with 3 little sliders, you can tell that she's about to cry. And, this is or maybe she smoked something, but it is, there's something psychologically wrong with this woman at this moment. So, when we started developing this eye project, we kept running into this wall of people saying to us, but eyes in the game, they're only 3 pixels, nobody's going to ever look at them. Well, now, the video game designers are getting closer. It's like, it looks wrong. Why does it look wrong? And this is inside our company. So because we enabled them to do this thing, now they actually want to get in closer than we can possibly see ourselves, which is a little bit interesting because you cannot see. I mean, maybe a 3-year-old can, but I cannot see that. So. I guess that concludes this. There is one more speaker, Hal, but I wanted to link the entire presentation together, all the presentations together. We started with Paul and Paul's group, who has been for many years working, and most of his results are going towards film, or have been going towards film, and to beautiful results there. Concentrating on the very high resolution data, we take that same approach, but we say, okay, well, how can we compress animation? How can we compress the shading just so it fits in game? And then what Hao is going to talk about is actually, I find it fascinating because we are at the age of devices. Surprise devices coming every day. When I started working on projects, this thing on faces, this thing didn't exist. There were no smartphones, right? So with that, I will leave it to Hao, and this is all yours. We have to unplug. Yes.
Right, so we're running a little late, so what I'm going to do is I'm going to skip a few slides maybe, and I'll basically give you a little glimpse of what to expect maybe in the future. And to do so, I'd like to give a little overview of what has happened from a perspective of capture. So what we've seen right now is a huge technical overview of how to do realistic facial animation. And it's no surprise that we've already witnessing those things in video games nowadays. So here's a nice example from Crytek, Microsoft's Rise, Son of Rome. So I think we're really approaching the uncanny valley right now, and probably in a few years or even sooner, they will be really indistinguishable from reality. What is the next step? Well, facial capture. So in terms of facial capture, a lot of process is still very slow. Unlike in Canada, the degrees of freedom of faces are usually larger. So here's a nice example of recent work from Weta Digital from Dawn's of the Planet of the Apes. So here's a really excellent example of how much it matters to capture the facial details, the expression details of the specific actor, right? And very often you want to retarget it on a very different creature, something with a different anatomy. And getting that right is also very important, but the central point is you need to capture the actor's performance. So one way to do so is to use mocap, so to use markers applied on faces combined with the helmet camera. Here's a state-of-the-art work presented at last year's SEA from ILM, from Kiran Bhatt. And the thing that they're doing differently than before is that they're using contours in addition to just like dots. And the reason why this is important is that you're capturing much more from an actor than by just using a lot of points and by trying to synthesize details through a pre-computed rig. There's a lot of research going on how to handle all these things without markers since a decade. These are some early work from George Borshikov, as you may know from universal capture used for the Matrix. Later on, I did some work on trying to explore how can we use depth sensors in order to get facial details without using markers, right? So you can get a dense 3D reconstruction and you can do some tracking with it. Later on, Disney Research presented some work on how to combine depth and textures together. And I think it's also moving toward how can we do all these things together with just a monocular texture camera. So here's an excellent work from Max Planck Institute from SIGGRAPH Asia last year. However, even if you can get the really nice tracking, right, from lower and lower impact sensors, the question is also how can you cross the uncanny valley, right? So the example from the Curious Case of Benjamin Button really shows that the importance that we still need artists in order to fix the little things that you still can't capture, right? So it has been pointed out before, how about sticky lips? How about, eye regions? All these regions are still modeled in the rig because you don't have a good way to, track these occluded parts. So this is like still ongoing research, but just to give you an idea, this is still in the past. Nowadays, we're probably a little faster in order to create animation, but it still isn't fully automatic and still takes some artist time. At the other extreme is how can we make extremely fast capture? And fast capture means real-time capture. And why do we even care about that? Well, first of all, obviously, you can improve production, scalability, efficiency. So VFX, game production, you can give the director the tool that he wants. He can see in real time what is happening on the digital character. They can give you, other types of applications like virtual avatars, new types of natural interfaces, in-game experiences. And obviously, not only to create robots that look like human, but it basically is a way to give machines a human scale understanding of what a person is actually doing, right? So if we were to interact with robots someday, the robots have to perceive what we're doing, and facial capture is actually a central goal of that. And obviously, this could open doors to different types of applications in the consumer level, not only for entertainment, but also, for virtual mirrors, makeup. People want to look better, Instagram type of things, et cetera, et cetera. So what did we do in order to make real-time facial capture? So in the early days, we did some early work with Thibaut Weise on a work at the SEA, which is basically using a real-time structural light system. Back in the days before the Kinect came out, we created some of the first real-time facial performance capture systems using a structural light system. So let me give you a quick overview what has been done from the depth sensor perspective. So in the beginning, we started with a structural light device, something that you would build in a research lab. And that was, as you've seen, one of the early works. And it required a lot of training data, right? So you need to build a PCA model, you need to perform thousands of different expressions. And later on, we wanted to make these things more useful for people, right? So first step is to reduce the amount of calibration that you needed. We introduced our work on example-based facial rigging in order to reduce the amount of calibration, something that if you heard about FaceShift, it's one of the components that actually used this technique. So later on, when the Kinect came out, depth sensors, I mean, the quality obviously isn't as good as those professional structural light system customized ones that you build in your lab. But you know, it's the first step, and hopefully in the coming years the resolution would get higher. But the first thing is, if we want to get these things into market, we need to find a way to have a stable tracking. So, and also we want to make it more convenient for users to build facial rigs, etc., etc. So that's sort of like the type of development that's going on. So the recent work from Boazis and coworkers even require no training at all. And all these things are implemented in this excellent software called FaceShift. And the idea here is really going from high-end VFX things into consumer-level products that should be made more accessible. However, on the pure video input side, so there's another direction that doesn't require depth sensors. I mean, they're still not so commonly available. That also gives you know, a very interesting perspective, because they're almost reaching the same level of quality. So it all started a little bit more in the computer vision community, where people need to do, you know, surveillance, tracking in the wild, unconstrained tracking. So people started to explore sparse features that are extremely reliable on faces, regardless of the condition, occlusions, lighting conditions. And there's some commercial solutions available that makes these things completely automatic, and you have an extremely high fidelity. So here's some work from ImageMetrix since 2011. And more recently, we can even do 3D capture from a single video in real time. So this has been demonstrated by Chow and coworkers at last year's SIGGRAPH. That requires a little amount of training, and at this year's SIGGRAPH, obviously the next step is to reduce completely the calibration step. So this is really, really fantastic work, where you basically just have a webcam, you calibrate a neutral face, you capture a neutral face, and that's it. You can have 3D facial capture in real time. So it's funny because, like, from RGB video input side, it's more like about getting more accuracy, more resolution, etc., etc. So this is a real quick pipeline overview on what is actually happening. So basically, you know, you have an input, you have an output, and what you want to do in the end, you want to retarget some digital character, right? So the first step is you want to do tracking. So you want to capture your own face, and you retarget it onto Yoda. So input and output on both sides. And the idea is that how can we solve the tracking problem? And the tracking problem isn't entirely solved. There's still a lot of things to be done, but we're getting closer and closer in the real-time aspect. So obviously, you know, this is just a rough level idea. So this is if you were to use depth sensors. If you're not using depth sensors, you also have to solve a structure from motion problem. But essentially, you recover rigid motions, the 60 degrees of freedom, and then you use blend shape. You've seen a lot of stuff on blend shapes or using bones. Here, basically, you're just extracting some coefficients, constrain them between 0, 1, or -1 and 1, depending on your taste. And one thing that we've figured out is that it's actually, you know, if you want to get into realism, it's really important to track every vertex. And sometimes you don't want to be constrained by the limited degrees of freedom of a blend shape model. You can always increase the number of blend shape model, but then your system might be under constrained. And in the case of, like, you know, real-time capture in the wild, when you only depend on a few features, you need something that can allow you to have something really fleshy on your face. And to achieve that, one thing you can do is to do a per vertex deformations from the geometry processing community. And there's some very efficient algorithms, for example, Laplacian deformations, where you basically just need to solve a sparse linear system in order to do these things. And we've demonstrated last year that you can actually capture these things in real time as well. So here's just to give you a little comparison on how it actually looks like, right? So basically, from our earlier work, if you're only using a linear system, you see that the expressions aren't that expressive as if you were use you know, something that's per vertex, based on per vertex deformations. So let me just give you a quick, show you a quick video of last year's SIGGRAPH paper. You can see, focus really on the blue face, right? So you can see that there's really a lot of fleshiness in the face. And that's really due to the fact that we're actually tracking, we're combining, the lower resolution depth sensors with the high resolution textures. And the texture is not only driving a low resolution blend shape model, but also using, per vertex deformations in order to achieve that. Another important thing, of course, is to do a fast. Ooh, what happened here? Okay, well, that doesn't look good. Okay. Okay, we're tripping. Let me. Okay, that's the problem. Oh, it's not my problem, actually.
Could it be a resolution problem? Because we have to lower the.
Oh, you had to lower the resolution?
Yeah.
Okay, let me try that, sir. But I'm not even plugging in.
Yeah.
So. Sorry about that.